Hello and welcome to another video. So this one's going to be a little bit different. It sits a little bit between being a tutorial and also being a sort of behind the scenes look. So in this case it's at a project that's currently a work in progress one, and there's a number of systems that I've had to put together for it that I think aren't sort of enough that they would be worth sort of a full tutorial on their own, but I think are still useful ones to share, and I will make parts of this code available so that if you're running into similar situations that you can actually reference those as a bit of a solution, and also talk through a little bit of my sort of tech process and how I've approached sort of the problems that I'm trying to solve with this. So let's dive on in. So the setup that I've got, and I'll actually stop this and switch it to this other mode. So what this is a game that is going to be essentially a infinite runner, except you are moving along this procedurally generated canyon. Now, obviously at the moment, these are all just very placeholder blocks. There's going to be a lot more variation between things there. But I wanted to get that sort of baseline generation side sorted first. And the reason being was that I was pretty sure that it was likely going to be one of the big technical limitations that I might run into. That's sort of a large chunk of what I want to talk about at this stage. So in terms of with this, things that I know from doing this sort of in similar things before, things that I know that are likely to get expensive is the amount of geometry that I'm potentially going to be needing to render is potentially a factor there. The other thing there is also, okay, as well as just a lot of stuff to render, if this is a procedurally generated environment, and in particular, if it's an infinite one, then I'm faced with the situation of, okay, how much of the world do I keep around? Am I needing to be able to restore stuff? And in the case of this, I am, because as well as being able to move forward in the world, you can also move backwards. And while I'm not doing any sort of saving, I do want the geometry, the terrain, things like of that to look the same if you go backwards as what was there before. So that sort of added complexity to stuff. And a big part of that is because I'm continually then spawning and respawning things. So if we take a look and I zoom out, we'll be able to see this much more clearly. But so that's how much of the world currently exists in this. And if I start moving, what we'll see is sections dropping off and new sections being spawned in. Now, obviously, the faster you do that, the bigger the overhead that you run into. So there's a lot of factors there that make it get quite expensive. So object pooling is one of those things that I expect I'm going to need with this, but that I haven't actually set up yet, kind of intentionally. With how I'm structuring this is I'm wanting to make it that that's an option that I can turn on so that I can test my code with and without the object pooling, because I'm pretty confident it's going to make a big difference, but I want to actually be able to more easily quantify that. I want to be able to profile it with and without and easily toggle between. So that's been an intentional choice with this, just to give me a bit of options there and a bit more in-depth sort of stats from it. The other thing with this is rendering like of this, there's a lot of geometry that I'm sending that I don't need to. Like if we look at the moment, these are just all cubes. So things like the lower faces of these that are never going to be used. We're never going to render those. So for the geometry here, 1/6 of the geometry will never actually be seen. And it actually ends up being quite a lot more than that. So that was something that I wanted to find a solution for. So with that, there's a few different options. one option is I could build a lot of different versions of the meshes, and I could probably do stuff on the exporter side, maybe to export specific faces, things like that. But that gets messy doing a lot of that. That felt like a lot of overhead compared to I just want to be able to build the cubes, build them correctly, and then have that handled in a simpler way. That was a big part of what I wanted to be able to do. So what I actually set up, and I'll go to the scene where I have this, I created this cell capture stage, which initially the scene looks pretty much completely empty. But I have a whole bunch of hidden cameras. And what happens is I have this block model processor, and it has an awareness of the cameras. It also has essentially, okay, here is the texture size that I want to generate for when I capture things. And here is what the actual physical block size is. So if I run this, and what I'll do is I'm also going to turn on this debug spawn after generating. Actually, I won't turn that on first. Initially, I'll just run this. And so we don't really see anything. But if I had a look at the stage center, I've got this object there. So this is actually from a mesh that I just built. This was intentionally a mesh that I labeled every face. So each face has a unique marker on it so that I can uniquely identify it. I also textured it so that it actually has this black border that's a narrow border at the edge of every one. That was so that I could make sure that everything was getting lined up really precisely and that I could debug if I had particular faces being drawn, but other ones not being drawn. And what this thing does is those capture cameras, it loads the model, then it does a capture of a texture with each of those cameras, and it constructs those then into a atlas texture. And what it also does is it generates an actual corresponding mesh with the correct UVs. But if we take a look at the visual asset that it outputs, we have this. So it, for every possible combination of which faces are present, generates a unique mesh, gives it a name, and it embeds it into this scriptable object. So this is something that if you've imported your FBX models from other sources or just ones that you've been working on yourself, you may have already seen this fact that some assets you'll see things embedded under them. And so this is something that you can do. So this test here, this block visual asset, it's a scriptable object, but it's a scriptable object that I have then attached these individual meshes to so that it's all self-contained. Because what that allows me to then do, if I go back to that other scene, now I'm going to initially run this with my optimization turned off. So it's not using those procedurally constructed meshes. So we can see with this, batches is about 30,000, 31,000 euro. We've got about 750k verts and 373k triangles. And we sit without anything happening, sitting at around, generally anywhere from 95 to 115, 120 FPS. When we start moving, we see a much bigger drop. It's generally sort of sitting mid to low 60 FPS. Triangles and verts aren't changing much, but the FPS itself takes a fair bit of a hit. Now, if I turn on this optimized mesh drawing, which we already knew that a sixth of the faces being drawn were never going to be rendered. So with this, well, okay, the batches, it's a tiny amount less, it's pretty trivial. FPS sits around the same while we're stationary, but the number of tries has gone from 370k down to 73k. So a huge reduction in the number of tries. Verts as well, unsurprisingly. Our verts was sitting around 750. It's now sitting around 150k. So a significantly smaller amount of geometry actually needing to be sent. And when we're stationary, we don't notice much of a difference. But when I'm moving, big difference here in the FPS. Before, with all of the extra geometry and everything, we were tending to sit around sort of mid to low 60s. With this, we tend to sit around 80 FPS. So pretty good. It still does drop down below 75, things like that occasionally, but pretty infrequently. It's generally holding pretty good. And I suspect a lot of the sort of hiccups that are happening there are happening due to the sort of object pooling not currently being implemented. So it makes a big difference in the amount of geometry we're needing to send. Means also, part of it is if I take a look, visually we can't see any difference when we're looking from here. But if I go here, there's a lot of stuff that we don't see because we just have not actually generated it. So it makes it a lot more efficient in that regard. We can easily, this was why I had all of the unique face IDs there to make it easy to diagnose this and see, okay, are things oriented correctly? So that's good. So let's look at a little bit of how does this actually all work. So if I go back to the cell capture stage, this is kind of a pretty important aspect of it. And this is one of the sections of code that I am going to make available is this file in its entirety. I think there's a few files that I'll just provide the entire file in its entirety. With this one, what I'll also probably do is export a package because the scene itself is useful to have. So I'll probably export a package that has that actual capture scene and everything in it. So, in terms of how it's set up and how it works, a couple of sort of things. So, stage configuration, all of those things are pretty straightforward. Now, I get a list of all of the block models here. At the moment, I'm only processing the first one. So like I said, this is still work in progress. Once I actually have lots of models, I'm then going to be able to do this and essentially run these two functions for each of those models that are present. So quite intentionally with how I was structuring this, I was structuring it from the point of view of, okay, I know I am going to need to run this over multiple things, but I don't want to do that initially. I don't have multiple ones to run it over. So I just wanted to make sure I'm passing in all of the info. So structuring it the way that I want to use it in future, rather than I could just simplify a lot of this stuff and have done a lot of these things in a single function or all in here. But I wanted to do that modularity from the beginning. Makes it cleaner code, makes my life easier. Here, resetting the stage is straightforward. Again, not a thing that really comes into play much, but when we've got multiple of these being processed, will actually be helpful. So the first thing it does is it instantiates that prefab, that FBX that's set up there. It configures it with a couple of things. So one of the things it does is it does actually get the texture from that. And it does that so that it can actually swap the material. So this was, again, one of the things that needed to handle with this is if I just take that actual block model and bring it in, and if I captured from that, then we can already kind of see what one of the problems that we could hit is. See how this face is a little bit darker, and this one's really bright. So lighting becomes a factor. So very intentionally, this actually has a specific material for capturing that uses the unlit mode shader. That way, and that's why it sort of swaps it in, is so that when I capture it, I get an accurate recreation of what the actual texture is on that particular block. Now, there's probably stuff I could have done of post-processing the model and filtered out faces with that, but this was, the reason I went for this approach is largely it was tapping into things that I have done before, I'm familiar with, I'm comfortable with, like the mesh generation. So, okay, the capture itself, well, I know I'm going to get 6 textures out of it. So again, what I would do is each of these were captured separately. So that was a reproducible thing. Now I'm going to jump to that capture before I come back to this atlas texture, because there's a couple of important things with this. So when it's capturing, firstly, it would shut off all the cameras. It would configure all of the things like the render texture. It would configure the texture that the actual sort of capture is going to then get transferred over into. We do logic that you've potentially seen before if you've looked at stuff for capturing things with a render texture. Now, this was an important thing because initially, how I wrote this was how I've recently worked with render textures. So a lot of the recent stuff I've done with render textures, I've been using them directly in a custom shader, which means with that, I can use this graphics.copy texture interface because textures can exist CPU side or GPU side, and something like a texture 2D often actually is in both. And if you work just GPU side, that's way faster. That transfer from CPU to GPU or from GPU to CPU is slower. So we try to avoid those transitions if we can. So initially I was using graphics copy texture and then was trying to use this atlas generation that's built in from those textures. The problem was when you use graphics copy texture into a new texture 2D, that texture only exists GPU side. The Atlas packing works CPU side. So initially what was happening was my Atlas texture was always blank because there was no data CPU side. So while this is slower to do this approach of doing the read pixels and apply, this process brings it into the CPU side, so the actual Atlas generation works. So that's the reason why I'm doing this, and just something to watch for if you are working with Atlas generation, because this is a pretty useful thing. Packs everything into a single texture so that it takes up, you can use that one thing for lots and lots of different meshes. So really useful, really handy, but runs CPU side. So if you are getting blank textures out of this, that is one of the things to check, is if you are doing stuff with render textures, making sure that you are bringing that data onto CPU side. So, okay, creates the Atlas texture. So when we pack that, we get out a set of UV coordinates, which is really handy. Then we're creating this block visual asset. So this creates the actual scriptable object in memory. Then I create the actual asset on disk. And then what it does is it does this post-build logic and another save. So we'll take a look and see what these particular ones do. We'll look at the post-build first. So if you remember me showing earlier, this had those meshes embedded under it. The reason there is that when you have a serialized field linking to a mesh, that's going to be trying to link to an asset. It can't just link to a mesh that you've got sitting in memory. So procedurally generating the meshes, what was happening before I did any of this logic was I would procedurally generate the mesh, and then I would do all of the linking up. It would populate all of the entries, and the dictionary that gets built up, because this is a dictionary here, all of these entries, they'd have the correct key, but the actual value would be empty because what they were linking to was in memory. It wasn't actually saved out anywhere. So what I did was I changed this. So now that atlas texture is there in memory as an asset, but then I add it to this. I do the same thing with every single mesh. That's how I attach those into the scriptable object itself. So this post build is once I've created that visual asset scriptable object, it then goes and attaches my textures, everything there that is currently being referenced by it gets attached into it so that then when I do a save, it actually saves out the entire thing as one complete set. So this can be really handy for keeping things neat if you've got a lot of, complex data there in scriptable objects, a lot of extra things. That ability to attach an asset into another one, really, really handy. It's a really, really powerful thing. It's a feature I haven't actually used before until now, but is one that I'm definitely going to make a lot more use of in future because I think it's incredibly valuable. So that's how that part works. But the key part really is the geometry generation. So if I go to that, so when we go to build it, creating the instance for the scriptable object, straightforward. We've seen that process in a lot of cases. The atlas texture we've already constructed, the meshes, we're just newing everything, and we just store our size. Now, how I worked with the faces, because I wanted to make sure it generates every single one. So what I did is I made this a flags enum, and each face corresponds to a unique bit. And then just as a helper, I have an all value that corresponds to all of those bits being set. What that means is that I can absolutely reliably know that I will have covered every single permutation of faces if I do a count. As we'll see here, I count up from 1, because we don't need to do it for the first one where there is no faces. But if I go all of the way up to having all of the bits set, which actually, that should probably be less than or equal to, I'm pretty sure, because there should be 256 entries. I have a feeling it might not have all of them. Because, yeah, I'm pretty sure, left, right, back, top, bottom, if I run this again, I'll probably find that there is an additional one. And there is. Everything's set. Cool. So, important aspect there with that. I'll make sure I save that. So, if I count from 1 up to and including having all the bits set, then I know I've covered every permutation. So it being a cube does make that easier. So if you were doing this with something more complicated, that would be trickier, but as long as it's with a cube, it makes it straightforward. Then I go and I generate the individual faces. So these, because it was pretty similar for what was needing to happen, I set up some helper functions. And if we take a look then at what those were doing, is I'd populate the vertices. Now there was a little bit of trial and error with some of the stuff like the UVs and the vertices there, just because it's easy to, they have to be in what's called a specific winding. So winding is either going to be clockwise or counterclockwise, and winding is what gets used essentially to determine whether something is forward facing or backwards facing, for determining whether it's getting culled or not. So with this, there was a little bit of stuff where I thought I'd gotten them around the right way, and then I test it and it wouldn't be around the right way. Similar with the UVs getting them flipped. But that's why what I had this debug spawn after generation, which this might go a little bit, nutso with how it might look. So we'd have that test block, but then I had these individual faces. So this was sort of how I was checking everything was perfectly lined up. Was making sure that it matched with the spawned in block. So again, just double checking it at this stage and not just assuming it was going to be correct and then finding out later there was a huge issue. So I had separate helper functions for each of these. So that worked out quite straightforward. And because the building of the triangles for a particular mesh is the same process in every single case, what I did was those just get actually generated separately. It's the one function because it's deterministic with I'm putting the triangles all in, the vertices for them in a set way, so I can always just actually do this generation in the same sort of set way. So that worked quite nicely. Now, with this, there is definitely room for being able to make some of this more efficient in terms of, okay, different blocks will have different textures, but the actual meshes will look exactly the same. So likely at a later stage, what I will end up doing is some further refinement to this, where I have one set of those meshes that all of the blocks use, rather than actually having a per block set of meshes. Now, it's a very tiny amount of data, but again, anything to minimize the amount of data and also anything to make it that it's essentially a simpler set of information that it's needing to keep in memory, needing to share with the GPU. Because if I have 500 different blocks, but they all can use the exact same mesh set, that heavily reduces the amount of things that need to be kept in memory, which is good. So that is a further refinement that I'm likely going to be making to it. Now, that's sort of how that general process worked, but then it's kind of got to fit in with the rest of this, because when I go and spawn things, I need to know whether they need the full sort of which faces they essentially need. Do they need the majority of them? Do they only need one? What do they actually need? So that happens here in the coordinator. So I have this logic for determining what faces a cell needs to have. Now, because we are dealing with a dynamic environment, as things get newly spawned or despawned, what flags need to be present can actually potentially change. So that's something where I need to potentially update ones. So I've done that where, okay, if it was spawned and the flags have changed, then it does despawn it. and that determine cell faces, we periodically run that whenever we know that we have new ones to spawn. So in the update logic here, so in update, we have if there were pending spawns, then we do a reclassify, and then we handle the actual spawning logic. So again, I originally did have this more integrated with other sections of the logic, but what I wanted to do was split it out so that I have clear central points for actually feeding in stuff like the object pooling. So this will eventually feed into the object pooling. Same with, at the moment, that despawn and respawn is necessary for the ones using just a full prefab. But for ones where it's a mesh change, I actually could just change the mesh on the mesh renderer. That would be all it would need to do. It wouldn't actually need to despawn and respawn it. So there is some efficiencies that could be gained with that. So, okay, that's sort of the rendering optimization side of this. But something that I think is worth looking at also, because I think it's quite relevant, is how do I actually manage the procedural generation? In particular, this idea of being able to go forwards and backwards and have the environment, not necessarily the state that things are in, but the environment be consistent. So if we take a look at how this is structured, so I have these spans, and we can see an individual span here. So this does illustrate one of the things that it never used to be a priority for me, but is these days because it helps so much with clarity. If you're doing procedurally generated things, make sure that you are setting the name as part of the procedural generation. That's why I did stuff to actually name all of the individual meshes. So if you look at these, everything has a very clear name, all the way down to the texture atlas. So keeping everything clearly named just makes life a lot easier, makes everything just much more manageable. So I have my spans. So things get spawned in these spans. And within a span, I have columns. And then columns have individual cells within them. So what I wanted to have with this is essentially as you progress further through the level, so as you move further to the, in this case, the right of the screen, as you do that, the environments will need to change. So there is biomes factored as part of this. The other thing that happens there is the difficulty should increase. So there's this concept of essentially a progression factor and so forth. So what I did, if we take a look at the sort of spawning. So we do have this initial sort of world building and setup. So again, I have support for seeding the random number generator. I keep track of these different noise offsets. I'm making use of Perlin noise a lot, but I want there to be variations with each playthrough. So based on the RNG that you set, it then generates a bunch of random offsets for various configurations here. And these get used for different purposes. So what I then do, and the progression factor and things like that are a big part of this, is, okay, initially when I'm building the world, and this is just sort of the initial beginning setup, the progression factor starts at 0. We generate through all of those spans that need to exist. And I have this concept of being able to generate a span moving forwards or generating backwards. Now within a span, the progression factor will change. So each progressive span that it spawns, the progression factor, it knows what the previous one was and it builds off of that. So it can always work forwards and work backwards. Now if we take a look at that particular span generation, so okay, in terms of a couple of things it does, it obviously creates that actual span, it stores X coordinates, things like of that. So basic positional information. And we do kind of have two coordinate systems coexisting here. We have a integerized coordinate system in terms of what span something is in, what column it is in, what index it is in, and also then the corresponding world position. So again, I generate the columns here left to right, and I keep track of, okay, well, here's what the starting progression factor is, and it processes that. So let's look at what generate column does. So it knows the X here that it has. So it knows what the starting X was, and it knows what the column X was. So what it then does is it will go and step through. It updates that noise. So we get that offset being applied here as well. So it steps through all of that. And then what it does with these other ones is we have our other noise offsets that get used. So that determines our ceiling and floor height. We have our intensity factor and our progression factor. So they all sort of tie in together. And that has a general scale that we can ramp things up or decrease them if we need to. And then it updates the progression factor based upon whatever it's pulled out for the particular delta values that we've calculated. So this column noise X is always going to be deterministic and is always going to, like, it monotonically increases. So as you move forwards, it's always going to be stepping up. So it's not relative within a span. It is also with this, and we can see that if we look, when we've run this, if we look at our dynamic root, the columns here, that X is part of the name, and so it always scales up or down. It doesn't reset within a span. So it means these, I can reliably be calculating what those factors are at each particular point, which is really handy. Those get stored within the individual columns. So we have our intensity and progression factors, and then we just do the generation here is pretty straightforward. We're just picking sort of the depth that stuff appears at. That's pretty constrained. So there's not a lot to that side of it. It's just a lot of careful tracking of the particular values and everything within a span. When I go to close a span, what I do is I process all of the columns within that, and I make sure I store out things like, okay, what's the overall intensity factor, essentially the average intensity factor for that span? What is the starting and ending progression factor? Because that makes it easy for me needing to generate the backwards ones. Because if I then go back further down, because we had our generate span forwards, generating it backwards, the process is largely pretty similar between forwards and backwards. But there's a couple of things that sort of need to change. We need to do a little bit of adjusting for what our starting and ending X are. We need to still do the spawning in effectively the same way. The span and everything still gets created the same way. We still create the columns similarly, though we're doing a minus of our x factor rather than a plus. Progression factors, things like of that, are still similar. But what we do at the end is we actually flip it. Because when we add these columns in, they are going into the list that is stored internally in order, but actually the order that we are generating these in is backwards, but that's intentional because we want to be stepping it back bit by bit by bit. So that is an intentional thing, but we just flip it at the end, so then they're in the correct order. Which if we take a look at what that does, it's pretty straightforward. Doesn't need to do anything particularly fancy. So it's just organizing the data so everything is laid out data-wise in a consistent way. Because it was spawning things at the correct location, just needed to make sure that it was actually storing the data in the correct way. That allows us to go forwards and backwards. Now when it's actually running, that was a little bit involved. We needed to work with our movement to figure out, okay, how much had we moved by? And one of the big things was, are we in a different span? Because that actually is really important. Because if we're in a different span, then we need to go and actually spawn and despawn ones. So we've always got our buffer present. So what it was doing was checking, okay, have we hit the threshold where we need to spawn? And then it could do its spawning logic. Otherwise, it could do its despawning logic. So pretty straightforward with that. And then what it would do is it actually moves the world. So the player can actually move, but if I select the stationary route, and we look at the player avatar. So the player avatar is there. They can move, and we can see the values changing in the inspector. But if I actually start us moving, so if I select our coordinator and start it moving, our stationary route obviously doesn't change, and our player, their location doesn't change either. So that was a way of making it so that it could handle, because if you move too far away from the origin, you can get weird glitches due to floating point precision issues. Engines do have some tricks to work around that, and so there are ways of solving it, but in this case I didn't need to actually do that. I can just relocate things and slide them further back in terms of the locations they're trying to actually appear at. Now eventually that might be something where I do that slightly differently, but for now that seems to work quite well. We'll end up testing it at some point with running it for a very, very, very long time and at a very fast pace, just to make sure that nothing goes wrong with it. But that was a big part of how it was working. There's also, with this, we do have a bunch of boundaries in front and behind for it to collide with, so the player can't go out of the map. And the visual mesh does not have collision on it, very intentionally. It won't end up having collision on it. And the player avatar does have the collision. And the reason there is that when we go to rotate, what we'll see is, so we're rotating, and we see how the position is changing for the player avatar, but it's not rotating. The rotation is actually all done on the visual mesh. This was a very intentional thing. I wanted to decouple the collision side of things from the actual visual mesh so that I don't get weird bits of glitchy movement from the actual behavior there of it colliding into things, because I need it to be able to collide into things. Because if I run it, turn that off for now, just because it makes it a little bit easier to see. So this, I can hit things, which is good, and I can get caught on stuff, which is good, but it's able to get out of that. And it doesn't cause any weirdness with the actual visual animation sort of side of stuff itself. So that's good. And I do just have some debugging stuff there at the moment, so I know what cell it's actually hit into. So that's really the bulk of the systems there. The key stuff is that visual asset spawning and the setting up of that to allow me to use significantly less geometry, which means I can put those render resources elsewhere. It means I can have more complex visual assets in other places, and all of that generation of the meshes happens editor side, happens during the dev stages of it. It doesn't happen with the actual runtime build, which means there's no runtime cost for it, which again is great. It means that I've got that headroom there for being able to have things look cooler. So the game's still a bit away from actually being anything more than what you currently see. And that was because early on I did realize that these were pretty important tech issues that I needed to solve, and I needed to solve well, because otherwise the game was just never going to be viable. So that's why I wanted to get them solved first. So I will make some of the bits of this code available. There will be some bits that I probably can't make available, but I will make available as much of it as possible. And I will, as part of that, the actual scene here for doing the capture. So that cell capture stage, that is one that I will export a package for along with the code. So I'll put both of those in the repo. That'll just make it easier for actually if you're importing that into your own projects. So dive on in and check out the code that I've made available there. Check out the package that's been made available. See where you might want to use some of this in any of your own projects. At some point, this may end up being something where if I make a more generic, more reusable version of it, I'll turn that into something that's a standalone tutorial or asset that's available for people to just freely use. But at this stage, it's a little too tightly coupled with the game for it to be something that would make sense for being there as a standalone thing at the moment. But it is on my list to look at doing that in future. But as I said, dive on in and experiment with it. Thanks, folks. Hope you found that interesting and helpful. If you have, chuck in a like and subscribe. It really helps out. It's really appreciated. If you have any questions, chuck those in a comment below. If you're looking for the code that I mentioned, that's available up on GitHub, and there is a link to that in the description below. And if you're looking for other ways to support the channel, then I do have a Patreon, and there is a link to that in the description also. But until next time,